Here's a fascinating puzzle about triangles. We have a triangle with sides 7, 12, and 10, with a mysterious point D on the bottom edge. Our challenge is to determine exactly where D is located. These specific side lengths form a valid triangle, and they'll give us precisely the information we need to locate point D. Notice the line connecting A to D, which is called ACVN. This line divides our triangle into two smaller triangles. The point E marked on this line will be key to our solution. Let's look at the left triangle ABD in more detail. Notice the orange circle inside it. This is called an incircle. It's a special circle that touches all three sides of the triangle at exactly 1 point each, including our special point E on line AD. Let's examine where the incircle touches each side. Here's the tangent point on side AB and the one on side BD. And as you can see, the incircle touches our Sevian AD precisely at point E. When we look at the distance from vertex A to these tangent points, something remarkable happens. The distances from A to these points are exactly equal, including the distance to point E along our tangent line. This isn't coincidence, but a fundamental property of tangent lines from an external point to a circle. This tangent length has an elegant formula. From any vertex to the tangent points on adjacent sides, the distance equals the semi-perimeter of the triangle minus the opposite side. Now, let's examine the other triangle, ACD. It also has its own incircle, this blue circle that perfectly touches all three sides of triangle ACD. This second incircle touches side CD here, but now comes the magical moment. Where does it touch line AD? At exactly the same point E that we've been tracking all along. This is the key insight that will unlock our solution. Since both incircles touch AD at the same point E, we can calculate the distance AE two different ways, one from each triangle. These calculations must yield the same value, creating our constraint equation. From triangle ABD, the tangent length AE is determined by the orange incircle. From triangle ACD, the same segment has a value determined by the blue incircle. These two values must be equal. Now we can transform this beautiful geometric insight into algebra and watch the answer emerge naturally. Let's define our key formula. For any triangle, from any vertex to the tangent points or on adjacent sides, the distance equals the semi-perimeter minus the opposite side. This elegant formula states that the tangent length AE equals S minus A, where S is the semi-perimeter of the triangle and A is the side opposite to vertex A. For triangle ABD, let us calculate the semi-perimeter. It's half the sum of all three sides of the triangle. The side opposite to vertex A is BD. Using our tangent rule, AE equals the semi-perimeter minus BD. This simplifies to the following expression for AE. Similarly, for triangle ACD, we calculate the semi-perimeter as half the sum of all its sides. The side opposite to vertex A is CD. Using the tangent rule again, AE equals the semi-perimeter of triangle ACD minus CD. This simplifies to our second expression for AE. Since both expressions equal AE, they must equal each other. This gives us our constraint equation. Multiplying both sides by 2 to eliminate fractions, we get this expression. Notice that AD appears on both sides and cancels out. This gives us a simpler equation. Now, we can substitute what we know. AB is 7 and AC is 12. Since point D lies on segment BC, we know that BD plus CD equals BC, which is 10. From this, we can express CD in terms of BD. Now we substitute this expression for CD into our constraint equation. Let's expand the right side of this equation. Simplifying the right side, we get 7 minus BD equals 2 plus BD. Moving all BD terms to the right side, we get 7 minus 2 equals 2 times BD. Therefore, BD equals 5 halves, or 2.5 units. The mysterious point D sits exactly 2.5 units from point B. And that's the beauty of mathematics. What started as a simple question about a point's location revealed an elegant dance between incircles, tangent lengths, and algebraic constraints. The answer was hidden in the geometry all along.